lecture 11. We were talking about the dip pen type of direct write process. So here are two schematic drawings of this process where you have these dip pen that will dip and print these at extremely fine resolution distances. So you can have multiple pens all dipped in using different inks and depositing them on a substrate that need not always be flat and plain. So in this case, the one that I'm showing here is capable of producing 14 nanometer line widths with 5 nanometer spatial resolution. So you can see the extremely fine resolution that you can get with these kinds of dip pens. And you can get, it is typically used to produce these features on flat surface, although you can do that on non-flat surfaces also, but even then um, sometimes you may get uneven topography because of the very small differences in the heights of your surfaces. So um, in this case, you have some one-dimensional 8-pen designs. So they may do all that at the um, uh, same line deposition scheme, or they may change that so only some of those pens will be depositing and writing rather than all of them at the same time. So this is the dip pen nanolithography. So it is, say for example, it can be used for writing or placing down um, DNA molecules. So uh, it is to be noted that these pens and these materials must be stiffer than for most nano inks, if this is the case, because the DNA is inherently very viscous. So you have different kinds of um, possibilities. So in this case, Nano Ink, the company offers two types of inks. Um, the first one, I mean, they are both chemical in nature. So the first one is an acid, and the other one is a thiol. So depending upon the type of material that you want to develop, so you can have different kinds of um, pens. Next, let's look at an inkjet printing process. So inkjet printing process is used to form electronic circuitry on flat surfaces. Um, in this case, it might be difficult to put it down onto a conformal substrate. So it is very similar to the direct printing type of additive manufacturing. And what you have to do is you have to make sure that the print head and the motion control system are optimized for very high accuracy electronic traces from these direct write inks. Um, and you do not often, I mean, so most of the time you're only doing single line or maximum two lines. And you don't do that like building up three-dimensional objects. So you're only doing single line or multiple line, I mean two lines kind of a thing. Okay. So what are the benefits of these processes? The benefit is that it can be done extremely fast and it is not very expensive, and you can have parallel sets of multiple print heads. So if you do that, you can put down, you can print on very large areas extremely rapidly. And um, there are a lot of suppliers for inkjet print heads. Um, the one of the earliest examples is a company called Z Corp, um, and we talked about that in the initial introductory slides. And now Z Corp has been taken over by 3D Systems. So you can what they do is they take commercially available inkjet printing heads and attach that to. You take out the ink from this, and you sometimes put some kind of a liquid that is supplied by Z Corp or 3D Systems, and you can use that to deposit these uh, ink or materials onto surfaces. So, what are some of the difficulties? You have to use droplets as building blocks, and you may not always be able to print them on conformal surfaces. Conformal means, surfaces that are not flat, and extremely stringent requirement for proper ink rheology than other ink processes, and you only have a limited droplet size range, so which means that you can't build up a height for these materials. You can only have one layer or maximum two layers, because once it goes, it can kind of flow down from the previous surface, and you are not going to get very high resolution and nice feature sizes. Okay. The next kind is the aerosol based direct write. So in this case, these ink-like materials are suspended as an aerosol mist. So this one is an example is the aerosol jet process developed by Optomec. So in this case, you have a carrier gas, you have an atomizer, and that it goes in and deposits this material. And then you also need to have, sometimes these powders are pyrophoric, so you want to make sure that they are deposited and they are solidified almost instantaneously. And you also have sheath gas, because some of these powders are can be oxidized, so you do not want that to happen. So you want to have a gas masking the powders that are being deposited onto a substrate. You can also have a liquid molecular precursor or a colloidal suspension. Um, and it can have um, it can be used for many different types of materials, including metal, dielectric, ferrite, etc. And so you saw the schematic in the earlier one. And you can have a laser that is, after you place down the powder, you use a laser to um, process the deposit to the desired state. So what are some of the advantages? You can have extremely, you can put it down from a high standoff distance and large working distance. And you can have the nozzle between 1 and 5 millimeters with little variation in deposit shape and size. And it is much more flexible than inkjet printing. And you can have the material process a wide range of material viscosities. You can have layer thicknesses between 0.025 to 10 microns. So you can have extremely fine features and fine steps, so that you can have very good control on the dimensional accuracy of your part. But it is much more complex than compared to other ink-based processes, and Um, but in spite of its complexity, it is a pretty fast process because you can have more than one print head in an array. So you can put down much more material. So you can put down material like a tape rather than in tape form rather than in a powder form. So you can process these materials in extremely fast fashion. Okay. So these are some of the advantages and disadvantages of various direct write processes. So there are key benefits and key drawbacks. So this lists the whole thing for all these different processes. The next kind I want to bring to your attention is called laser transfer direct write. So in this case, you can have these materials absorb a high energy laser beam, absorb the energy from a high energy laser beam. So that energy can be used to heat, melt, or ablate, or some combination thereof. And when you are ablating that material, a gas or plasma is formed. And when you add more laser energy, it can expand very rapidly. So when that happens, it can create a shock wave and it can propel the material and it can is very accurately transferred in a repeatable and accurate manner from one location to another. Okay, so you can use this method to transfer the material from a foil, tape, or plate onto a substrate. So you do this, and then that gas or plasma will go and deposit onto a substrate. So that substrate might be upside down, and you can deposit this material. And if you can combine that with a masking process, you can use this to deposit that in very accurate manner. Okay, so this is a schematic of that laser transfer direct write process. So one of these processes is called maple. So you do this and you micro machine the packet uh, and then that can deposit onto the bottom of this plate. So many different materials have been deposited using this process. So the disadvantage is that um, you need to form a tape with the appropriate transfer and deposit for depositing the materials, and the unused portions of the tape are typically wasted. But still, for materials that can easily form films, this is only a minor drawback. Thermal spray direct write um, was originally developed by SUNY at Stony Brook, and they commercialized that through a spin-off company called Mesoscribe. And because thermal spray is a very standard process for depositing materials at very high velocities and deposits them onto a substrate. And you can do that for a number of materials, especially ceramics. Um, and you can deposit them onto a substrate that is also a ceramic or a polymer or a metal. So here is a schematic of this thermal spray direct write. So you can see what I'm talking about. And you can deposit them in solid or semi-solid state. Um, so these materials can be deposited at or near room temperature, and it can be deposited as droplets or solidified platelets, and these solidified platelets are called splats. So you are splatting the material onto a substrate, and your processing conditions and processing parameters will strongly control the deposit microstructure and its properties. So what are some of the key characteristics or key advantages is that you can deposit this material at a very high rate. You can do this for multiple materials, a very flexible type of process, and in the as deposited stage itself, you can have very good material properties, and it can moderate the thermal input during the processing. So you can deposit that on a variety